Swayam Prabha. Digital India. Educated India.
Today we'll discuss about special random variables. So it will be a continuation of what we discussed in our previous lecture. So if you remember, in the previous lecture we started with famous inequalities, namely the Markov's inequality and Chebyshev's inequality. After that we started discussing about special random variables. So those are the random variables which we see widely in our day-to-day life. Okay, so they are widely used in many random experiments, and in the process we started with special type of discrete random variables where we discussed about binomial random variable, geometric random variable, and negative binomial random variable. So today we'll just continue our discussion with the random variables. So we'll again discuss two more discrete random variables and then we'll jump to the continuous ones. Okay. So today we'll discuss about the hypergeometric random variable and Poisson random variable. Both these two types of random variables belong to the discrete class, and then among the continuous random variables we'll discuss uniform random variable and exponential random variable. So let's start with hypergeometric random variable. So let us just first take some example, because it's a very simple random variable and as such you don't need any definition to calculate the probabilities. So let's say in day-to-day production processes, let's say we have a day-to-day production processes where many manufacturing units produce lot of parts. Let it be in semiconductor industry, let it be in any manufacturing industries. Okay, and let's say in a particular day, on day-to-day basis, they produce n parts. Okay, now some manufactured parts, let's say y among those n parts produced, they do not conform to, let's say, quality control criteria or customer requirements. Okay, and let us suppose, and in those n parts we have some parts which are defective and many parts which are good. Okay, that happens in typical production processes. So let us suppose that you select two parts randomly without replacement from the day's production. Okay, now, that is selected units. Whatever selected units are not replaced before the next selection is made. So let A and B denote the events that the first and second parts are non-conforming to the quality control criteria respectively. Okay, so we know from the conditional probability thing that with the knowledge that the first part is non-conforming suggests that it is less likely that the second part selected is non-conforming. Okay, so this experiment, whatever this simple experiment, is fundamentally different from the examples based on binomial distribution. So in this experiment the trials are not independent. Note that in the unusual case that each unit selected is replaced before the next selection, the trials are independent and there is a constant probability of a non-conforming part on each trial. Okay, then the number of non-conforming parts in the sample becomes a binomial distribution, right? Binomial random variable. However, in this case where the samples are which are often selected without replacement. Okay, so in such a case where you select randomly and then define your success, whether that is defective or non-defective depending upon what sort of experiment you are doing, so then calculating probabilities become a bit tricky. I mean, one can easily determine by simple reasoning, but a general formula for computing probabilities when samples are selected without replacement is quite useful. And then comes the hypergeometric random variable. So let us define it properly. So let's say a set of n objects contains k objects which are classified as successes. So it depends upon the person who is doing that random experiment to define his or her own success. Okay. Then that also implies that n minus k objects are classified as failures. Like there are like two types. So sample of size n is selected randomly without replacement, and this is very important, without replacement from n objects, where normally k, which you classify as your success, is less or equal to n, and also the number which you select randomly is also less than n. Okay, so let the random variable x denote the number of successes in the sample. Then x is a hypergeometric random variable. Okay, and from the typical probability distribution we can see that the mathematical formulation agrees with it, and it has three parameters, namely capital N, K and small n. And we can easily see that, although it's a bit tricky, but I would urge all of you to derive that the expectation value of such a random variable is NP, which is equivalent to what you had already got for your binomial random variable. See, there's a subtle difference between hypergeometric random variable and binomial random variable. Like if you would have done the similar experiment with replacement, like whatever you have chosen, that part or that number is again replaced, then your x would have been your typical random variable. Okay, here it is without replacement, so the next time you choose the other part or the other number, then probabilities change. So here please try to derive that the expectation value of such a random variable is n times p, which is equivalent to what we had got earlier for binomial random variable, and the variance is np times 1 minus p times another factor which is n minus n by n minus 1. This factor, this n minus capital N minus small n by capital N minus 1, is also called as finite population correction, okay, factor. And this is the only difference from the binomial variance. Like if you remember, for binomial random variable the variance is only np times 1 minus p, whereas for a hypergeometric random variable it is again multiplied by a factor n minus n by n minus 1. Okay, and p, which is k by n, k is your number of successes, by n, which is the total number of units or objects, can be interpreted as proportion of successes. Okay, so it is quite clear. Normally when we do our school level probability courses, we have seen such type of problems or such type of random, although we didn't know that it has a special name, but we just with simple reasoning we could solve this sort of probability calculations. Right, now let's just take a similar simple example of this probability of computing probability for hypergeometric random variable, and then we'll discuss about one of the most important discrete random variable, which is called Poisson random variable. And I would urge once again to all of you to calculate the expectation value and variance for this hypergeometric random variable. Okay, so now let's take a very simple example. Let's assume a batch of wafers contains 100 wafers from supplier A and 200 wafers from supplier B. If 4 parts are selected randomly and without replacement, so that you know that you have to do a hypergeometric random variable consideration, what is the probability that they are all from the supplier A? Okay, so here you have to estimate for p x is equal to 4, and in the numerator you select row 4 from 100 because it has to come from supplier A, times let's say 0 from 200, and in the denominator you have 4 from 300. Okay, 300 is the total number of wafers. And similarly you can calculate other two probabilities. Okay, so when it is x greater or equal to 2, you have to consider cases for x is equal to 2, 3 and 4. and calculate the individual probabilities and then add up to get the final probability. This is a discrete random variable. So you know how to compute probability. You know the probability mass function and you just have to use them. Then you have to calculate from x greater or equal to 1. So you can either calculate individual probabilities, otherwise the easier way is that 1 minus p x is equal to 0. So you just have to calculate one term and subtract it from 1 to get the final probability. Okay. Now let's talk about Poisson random variable. Okay, let us define this and then we'll try to understand why we get such a probability mass function and what are the processes which come under this Poisson random variable. Okay, so given an interval of real numbers, assume counts occur at random throughout the interval. Okay, so the counts can be anything like number of students arriving, number of defects in a sample, or number of accidents happening, number of persons suffering from a certain disease, and you can have myriad of examples which either occurs in day-to-day life or there are many examples which are very specific to engineering and typical basic sciences. Okay. Now, if the interval can be partitioned into sub-intervals of small enough length such that, okay, so you have to follow these conditions for a Poisson process, the probability of more than one count in a sub-interval is 0. So you have to ensure that, or let's say you have to divide your interval in such a manner, so you have to really make it into very small intervals so that the probability of more than one count in a sub-interval is 0. The probability of one count in a sub-interval is the same for all sub-intervals and proportional to the length of the sub-interval. And the count in each sub-interval is independent of other sub-intervals. Okay. Then the random experiment is called a Poisson process. So the way we define is the Poisson random variable, let's say x, that equals the number of counts in the interval is a Poisson random variable with parameter lambda greater than 0, and the probability mass function of x is given by the following mathematical formulation, that is e to the power minus lambda times lambda to the power x divided by x factorial, and your x takes integral value 0, 1, 2, 3, 4 because this is the count data, so you have integers. So this is the formal definition, but let us try to understand this Poisson process with an example and also try to understand why we get such a probability mass function. Okay. So let's try to understand the basis of this probability mass function with an example. So we know that flaws occur at random along the length of a copper wire. So we are taking a copper wire and we know that there can be surface defects and all that. Okay. So let's take one copper wire and we know that the defect or flaws can occur at random along the length of the copper wire, and let x denote the random variable that counts the number of flaws in a length of L millimeter of wire. Okay. So that is a random variable. You have to get the count of the number of flaws. So, and it's given then the average number of flaws in L is lambda. So that is the property, or let's say the characteristic of that copper wire, of the given copper wire, that on an average per mm in L okay, L millimeter, the number of flaws is lambda. Now the probability distribution of x can be found by the following reasoning. Okay. So what we can do, we can partition the length of the wire, that L millimeter, into n subintervals of sublength. So if you can divide that L millimeter into n subintervals of small length, let's say you can go to even micrometer level. And if the subinterval chosen is small enough, okay, then we can ensure that the probability that more than one flaw occurs in the subinterval is negligible. Further, we can interpret the assumption that flaws occur at random to imply that every subinterval has the same probability of containing a flaw. And let's say that probability is P. Now finally, if you assume that probability that a subinterval contains a flaw is independent of other subintervals, then we can model the distribution of x as approximately a binomial random variable. Right? So now you have n subintervals and you ensure that you do not have more than one count in a given subinterval, and then you have to find the number of counts. Okay, so then it essentially becomes your binomial random variable, right? So for every subinterval which would be your similar to your independent trial, so either you would find a flaw which you can term as your success, or you won't find a flaw, right, which you will term it as your failure. So each subintervals would act as your each independent Bernoulli trial, right? So observing either you would observe a flaw, otherwise you won't observe a flaw. Okay, so you have success and failure, and for each of the subintervals it is also independent. Okay, and then the probability of obtaining or seeing or detecting a flaw is also constant for all the subintervals. Okay, now then it becomes a binomial random variable. Okay, the assumption that flaw occurs at random implies that every subinterval has the same probability. So we can model the distribution of x. So if you remember, x counts the number of flaws as approximately a binomial random variable. Like, so the conditions, the way we have designed our conditions, so with those conditions we know that x can be treated as a binomial random variable. Okay, for whatever we are discussing now. Now with the present let's say conditions, let us try to understand more, and we know that the expectation value of a binomial random variable is n times p. Now what is an expectation value? It is mean of the random variable, and we know that the mean or the average number of flaws in LMM is lambda. This is the characteristic of that wire. Okay, it is given that it is lambda. So your lambda is n times p. So your p is lambda by n. Okay, so you can also say that, okay, the probability p, which is like probability of success, is lambda by n. So with small enough subintervals, so when you are telling your subintervals are very small, that also implies that your n is large. Okay, you have divided into large number of subintervals. So n is very large, or that makes your p very small, because p is lambda by n. Lambda is a constant, and when n becomes large, p becomes small. So we can write the binomial probability mass function. So it is ncx p to the power x times 1 minus p to the power n minus x. Okay, that is your typical binomial probability mass function. And now in the second step, we replace your let's say p by lambda by n. Okay, so this is what we are getting. Now supposedly that the number of subintervals increase, that means your n increases, and the probability of occurrence of flaws, that is p, decreases exactly because it is lambda by n, and it is such that then np remains constant because ex or the mean has to be constant. Okay, then it can be shown that, so just for n tends to infinity, like that your n becomes quite large, then it can be shown that the second expression will tend to e to the power minus lambda times lambda to the power x by x factorial. And this exercise, I think so all of you should be able to do that. Okay, so I have deliberately not put here because it is only 2-3 steps more, and then you can see that for this limit n going to very large values, or let's say you can put n tends to infinity, the second expression will tend to this e to the power minus lambda times lambda to the power x by x factorial. Okay, So, and this is your Poisson random variable. Okay. So now you should understand the Poisson process and how from a binomial, how this process is the limit of the binomial mass probability mass function when n is very large and p is very small. So that really makes it like a process for rare events, right? So when probability of seeing your successful event is very small, then that obviously becomes a rare event, right? When n is large and p is small, and you are trying to count those type of events, you have to look for those sort of events, then obviously those events are quite rare. So this distribution is many a times used to look for events that happens rarely. Okay. So, and this was a simple example that what should be the basis of such formulation of such mathematical formulation of the probability mass function, and it can be generalized to include a broad array of random experiments. Okay. So the interval that was partitioned in our example was a length of the wire. Okay. However, the same reasoning can be applied to any interval. It can be an interval of time, an area, or a volume. So it can be both spatial and temporal intervals. For example, counts of particles of contamination in semiconductor manufacturing, flaws in rows of textile, calls to a telephone exchange, power outrages, atomic particles emitted from a specimen. All those things has been very successfully modeled by this Poisson probability mass function. And also you should realize that if a Poisson random variable represents the number of counts in some interval, the mean of the random variable must equal the expected number of counts in the same length of interval. Okay, so if the length of the interval increases, the mean should also vary as per the increase, and you should be very careful about this aspect when using Poisson random variable. Okay, and this is the typical distribution of these random variables, and you can see it's a single parameter random variable, and you see that once you vary the value of the parameters, you see a significant change in the shape of the distribution. And right hand side shows the cumulative distribution function of a Poisson random variable, and you know what is the cumulative distribution. You can also calculate it for a Poisson random variable. Now let's see some of the properties of the Poisson random. These are not the properties, these are like the characteristics of the Poisson random variable. And from the expression of the probability mass function, you can easily see that it satisfies the two important criteria of being a probability mass function. Fx is greater than 0, and if you sum over x, fx for all values of its support, then it is 1, and that is the big thing about it being a probability mass function. And then we can also calculate the moment generating function for this Poisson random variable. From the definition of moment generating function, we know that it is the expectation value of e to the power tx, where x is your random variable, and we just use this conventional definition, and in place of x we put this, and just with little bit manipulation we can compute the moment generating function, and it comes to be exponential of lambda times e to the power t minus 1. And once we have moment generating functions, we can easily calculate the raw moments. So you can calculate the mean, which is the expectation value of this random variable, comes out to be lambda, and interestingly the variance of this distribution also comes out to be lambda. So it's a very interesting distribution because its mean and variance are equal. Okay, and it also becomes important. Okay, the mean and variance of a Poisson random variable are equal. So for example, if particle counts follow Poisson distribution, let's say with a mean of 49 particles per square centimeter. So the variance is also 49 and the standard deviation of the counts is 7 per square meter. Consequently, information on the variability is very easily obtained. Once you know the parameter lambda, you also know that that should be the variance of the distribution. So conversely, if the variance of count data is much greater than the mean of the same data, then you immediately know that you cannot apply Poisson distribution to model such a distribution, right? And also the Poisson distribution possesses the reproductive property which states that the sum of independent Poisson random variables is also a Poisson random variable. This is very easy to see. So let x1 and x2 be two independent Poisson random variables having respective means lambda 1 and lambda 2. That means these are the parameters associated with the Poisson random variable. So the moment generating function of x1 plus x2, because we have to know what distribution sum of independent Poisson variable follows, so we can just calculate the moment generating function of x1 plus x2, and while doing so we get the formulation as exponential lambda 1 plus lambda 2 times et minus 1, so which is the moment generating function of a Poisson random variable having mean lambda 1 plus lambda 2. Okay, so then that shows that sum of independent Poisson random variable is also a Poisson random variable. And from this also we can easily show that, we can easily prove another property, that if each of a Poisson number of events having mean lambda is independently classified as being one of the types. Let you classify with some types 1, 2, 3, 4 up to R types with respective probabilities P1, P2, PR, then the number of type 1 or type 2 or type R events are independent Poisson random variables with these respective means. So you can easily see from the previous property of reproductive property, and you can easily prove such a statement. Okay.